Hi, this is Dr. Viv. Let's talk now about scalar and vector fields and operators on them. The first video in this series, which will continue for a few videos, is the operator known as the gradient, and the gradient operator operates on scalar fields. The subsequent videos will talk about operators that operate on vector fields. What are scalar fields and vector fields? The word field suggests a field that's planted with something and there's one object at every point in space. So like a field of wheat. So there's wheat stalks everywhere and there's one wheat stalk at every point in space. You should think of it like that. A scalar field is a field where every point in space has got a number assigned to it. So XYZ is a point in space and it's got a number assigned to it. For example, the temperature at any point in the room is an example of a good scalar field, or a consistent scalar field, or the pressure at every point on the Earth's surface. A vector field is the same thing like a scalar field, except that each point has got a vector assigned to it. So you have three quantities, not just one quantity. So for example, the wind flow at any point on the Earth's surface would be a good example of the vector field, because at every point on the Earth's surface there's a wind velocity vector pointing in some direction, and the direction keeps changing and the magnitude keeps changing as you go from point to point. So a single point XYZ has got three separate quantities associated to it, each of which depends on X, Y, and Z. So that's the concept of a vector field. Now what I'm going to do now is talk about the gradient operator, and that operator. First, let's give some simple examples. Let me just offer you a couple of examples, and I'm making this up as I'm writing it. That's how common scalar fields and vector fields are. So how about x squared y minus 2z plus 5? That's a perfectly legitimate example of a scalar field. And a vector field, v of x, y, z, you can get wildly inventive here. How about tan xy I hat minus z over natural log of x plus y, okay, z to the 5, and then plus something else like e to the negative x squared times yz. You don't have to have all the x, y, z in each term, k hat. So that's an example of a particularly nasty looking vector field. You can just make anything up. There is no restriction on what V should look like. It can have singularities. It can have all kinds of bad behavior. We are not making any restrictions right now on whether the vector field should be differentiable or integrable, etc. Now, what about scalar fields like this? Scalar fields like that have an interesting feature. So if you try to plot a scalar field, actually it's quite difficult to plot a scalar field in 3 dimensions, because you'll need a 4th dimension to show what the value of phi is. So what we're going to do is temporarily restrict ourselves to 2-dimensional scalar fields. In other words, it'll be something like phi of x, y. And this allows the 3rd direction, z direction, to be used for plotting phi itself. So if I have the phi here and the x here and the y here, you can immediately see the problem in plotting phi of x, y, z. You cannot, because x, y, z are used up in our imagination, and the phi will have to advance in time. So that's a problem. You can do it with computers and create a movie at different times and stitch those movie frames together if you like. So first I'll create this assignment. So it's going to give you some sort of a, assuming for the moment this is a smooth function, scalar field, you're going to get a nice curve, 3-dimensional curve. Okay, it's like a hill. What we can do is we can think of equipotentials. Now phi, the scalar fields, first occurred in electromagnetism in what's called potential theory. So the study of equipotentials became very important, and so these level sets of constant phi values are still called equipotentials in mathematics. So equipotentials are basically constant height surfaces along the phi direction. So you can draw a few more. If you think of this as a hill, you have two equipotentials. Now, these are defined by the term phi, by the condition that phi equals constant. So just to make the example more concrete, I'll take an example here. Phi of x, y, z equals x squared plus y squared plus z squared. Now this is actually pretty easy to visualize. It's a sphere in 3 dimensions. So the equipotentials here are going to be phi equals constant. Now if I put constant values for this, I'm going to get the equations of spheres. For example, I get x squared plus y squared plus z squared equal to 5. Well, 5 can be written as root 5 squared. So that's actually a sphere of radius root 5. And if I put a different radius, I'll get a bigger sphere or a smaller sphere. So these spheres can be thought of as equipotentials. So here's what I meant by that stitching the movie concept. So at any given time, that sphere looks like that. At a different time, the sphere will look like that. And if you stitch all these pictures together, you'll get a full picture of the potential itself. So the equipotentials are like a stepping stone to understanding the true nature of the potentials graph. Now, I'm coming back to 2 dimensions from 3 dimensions to visualize it better. Here, the equipotentials are simply curves. There, the equipotentials were entire surfaces, and the transition between them was invisible to us. Here, the equipotentials are curves, and the transition between them can occur along lines joining these 2 curves. So for example, you can go like this down, or you can go like that up. The gradient operator actually plays a big role in making these transitions. So in the notes, I actually show you that if you pick any direction, say this pink arrow represents a certain direction, then in the notes I show the following. The rate of change of phi along the direction given by the scalar s. So what I'm doing here is the following. I'm taking a curve, okay, and that curve, if I call that curve gamma, depends on a parameter s. Now as I advance along the curve, there's a little ds vector that occurs there. That's the tangent vector to that curve. So the directional derivative, the rate of change of phi is all over the place, okay? Phi is just blessing this entire area. Now the rate of change of phi along this direction s is what I'm calling by d phi by ds. Now by the chain rule, this is just the rate of, the partial derivative of phi with respect to x times dx by ds. And similarly for the y and the z terms. This is sometimes called the chain rule in multivariable calculus. So when you took multivariable calculus, you learned corresponding operations in multivariable. And so what we can do now is dx by ds is just I can call it some quantity a times del by del x phi, plus similarly dy by dx is b times del by del y phi, and dz by ds is c times del by del z phi. So what I'm doing here is I'm essentially taking a straight line path for the small duration from here to here. I'm taking a straight line path, and that straight line path can be parameterized as x equals the change in x, like dx equals ads, and dy equals b ds, and dz equals c ds. So I'm making that a, b, and c are like little unit vectors that tell me how this ds vector relates to dx, dy, and dz. So that basically gives us our understanding. And so if that if I call this unit vector u hat, so u hat is abc, okay, then I can write this as u hat dot quantity, which I'm going to call the gradient operator acting on phi, because this is a dot product. So what I'm doing here is clubbing a, b, and c and dotting it with this quantity, which I'm calling del by del x, del by del y, del by del z, acting on phi. And this quantity is called the gradient operator, indicated by the Greek letter nabla, which is delta, the inversion of delta. So this is sometimes called nabla or upside down delta. Once you have that, let me write out a gradient operator in full. The gradient operator in ijk notation would be I hat times del by del x plus j hat times del by del y plus k hat times del by del z. If I write it in this form, it should make you a trifle uneasy because it looks pretty unstable. It looks like a bunch of hungry differential operators just hanging out there waiting for some food. And that food is a scalar field. Once you throw the scalar field at them, they give you something. Well, what do they actually give you? They actually tell you the direction of steepest ascent or descent along equipotentials. So that's one of the amazing things about the gradient vector. If I go from here to here, how do I go as quickly as possible? Now you all know when you're hiking, the quickest way to descend the hill that you have hiked is to simply tumble down. Well, when you tumble down, what your body is doing that you may not be aware of is, of course, you're getting pretty painful bruises along the way, but something else it's doing is that it is optimizing the gravitational potential for you as you fall. Nature always tries to minimize the gravitational potential as quickly as possible. So it's taking you down. So if you're Jack or Jill that tumble down the hill, it's taking you down the quickest route or the steepest descent. And this can be found because from this very expression that I wrote here, if I write d phi by ds, once again, as u dot the gradient of phi, I can always write this as the dot product. So that's the unit vector u times the magnitude of phi times cosine of theta. If I write it like that, the unit vector has got unit magnitude, so I'll just write it as gradient of phi magnitude times cosine theta. Well, this tells you that the maximum value occurs when theta is either 0 or pi. Okay, the maximum value occurs when it's 0 and minimum value when it's pi. So those are called the directions of steepest ascent and descent. The other thing you notice is interesting. When theta is 90 degrees, d phi by ds is actually 0. So that makes sense also, because when theta is 90 degrees, the rate of change of phi with respect to s is 0 because you are staying on the equipotential. So when you're staying on the equipotential, there is no rate of change of phi with respect to s. So all these things make sense for the gradient operator.